Okay, I think I'll start. It's a great pleasure to have Kerrie Mengersen here today to our Statistics Across Campus seminar. Kerrie Mengersen is a distinguished professor and director of the Center of Data Science at Queensland University of Technology. Among many other recognitions, Kerrie is a former national president of the Statistical Society of Australia, elected fellow of the Australian Academy of Science, elected fellow of the Australian Social Sciences Academy, elected fellow of the Institute of Mathematical Sciences, and elected fellow of the Royal Statistical Society. In her work, Kerrie develops methods in Bayesian statistics, hierarchical modeling, complex systems, and spatial-temporal modeling in order to solve complex problems in the real world. Those complex problems are in a wide range of fields, such as environment, health, industry, and genetics. Many of you might know her work on the Australian Cancer Atlas. Another project is around developing virtual reality environments for the prediction of locations of endangered species. Today, Kerrie's talk is about the dynamics of COVID-19, and I leave the rest to you, Kerrie.
Thank you very much, Muni. Can you hear me okay? And you can see my slides?
Yeah,
okay.
All good.
All right, thank you. Well, thanks very much for the invitation to talk in this this seminar series. It's great that we can have these communications and the engagement through this medium during this difficult time. And speaking of difficult times, this talk is about modelling the trajectories that arise from the cases in COVID-19. You can see on this slide here the list of authors that are involved in this study. So David Warren, a postdoc here at QUT, has really, I have to give him the kudos for this work. He's been driving this very capably and quickly in the last couple of months. Anthony Ebbett was from QUT and is now in Switzerland with Antonietta Mira, and then Chris Dravandi is at QUT as well. So this is our team, and I'd like to tell you about this work that we've been doing. Maybe I can get my slides to talk. Okay, so the world is at war with COVID-19. I don't need to tell you about this, but just to recap, we have the severe acute respiratory syndrome coronavirus 2. The first cases of this were reported in December 2019 in China, and it was officially declared a pandemic by the World Health Organization on the 11th of March 2020. So very quickly, we saw the numbers of cases explode around the world. The global tally by the 3rd of April was over 1 million cases and over 50,000 deaths. And by currently then, we have over 7 million cases. We have more than 400,000 deaths, and we have 216 countries with confirmed cases. So it really is a global pandemic. This is the total number of confirmed COVID cases and how quickly they're increasing. And this slide I've just put in here because it sort of shows where Australia is sitting with respect to the rest of the world. So you may be able to see the light grey lines, which represent the different countries. And you can see here the explosion of cases and then the tapering off for Australia. We're one of the very fortunate countries in being able to control the epidemic at very low numbers of cases, relatively low numbers of cases, and of course, relatively low number of deaths, although of course, every death is one death too many. This is our confirmed number of cases to the present day. And this is just highlighting also the note that's made here, which is the limited testing and challenges in the attribution of the cause of death. So one of the big challenges that we have in modeling these data is that the reported cases, the reported deaths, the reported recoveries are subject to some error in the reporting. So one of the major problems also then is in the testing, and I'll come to this a little later. So this means then that the numbers that are reported may not be an accurate count of the true number of deaths or the true number of cases from COVID-19. So when this started to explode, then there were many non-pharmaceutical weapons or approaches that were taken against COVID-19. For example, travel restrictions, hygiene, education, social distancing, school and business closures, and complete lockdown. So you can see on the right-hand side then just some of the changes that have happened in our public transport system, our mobility. This is mobility data for our public transport and workplaces at a national scale. The baseline there is at Friday the 24th of April, you can see the reduction from the normal baseline, so less than 40%, or around 40%, and then a slight increase over the last little while, but still much lower than what we've had before. So what we saw then was this peak, and now this decline, and now a slight peak, a slight rise again in mobility. And what we're looking for then is trying to track what's going to happen in the future, but learning about the future from the past. We can see here the difficulty in trying to model these data. This is the daily confirmed COVID-19 cases for Australia to the present time. So you can see the great peak that happened around March, and then we've tapered off. So we've done a great job nationally at being able to reduce the number of cases, daily cases, and of course the deaths. But we can see here the real need to be able to model and simulate, to be able to determine the efficacy of measures, and also to be able to quantify the risk, the patterns of increase and the patterns of reduction, in order to learn about future outbreaks and the severity of those outbreaks. Now, there are very many models that have been proposed for COVID-19. The literature is just awash with models and analyses of the COVID-19 data. And so our paper just contributes to that sea of papers. So there are models around the transmissibility, models about the global risk of spread through transport networks, forecasting and prediction, evaluation of interventions. And these approaches have been taken in, these analyses have been done in a number of ways, through empirical approaches, through statistical approaches, and through some mechanistic models with various extensions. Our approach that I'm going to tell you about, you can read if you read more details in the preprint that's on medRxiv. The paper's called "Hindsight is 2020 Vision," and characterization of the global response to the COVID-19 pandemic. So the model itself, let me tell you about it in summary. It's a stochastic epidemiological model within a Bayesian framework. We assume the true infected population is unobservable, and instead of modeling the interventions individually, we have this regulatory mechanism on the virus transmission process that captures the community response. So we don't want to have to include the actual interventions, because on a global scale, each country has those at different points. And also, there's also the question of when the intervention actually took effect, so what the actual latency period may be, and the community's adherence to that intervention as well. So there are many questions around how to model a particular intervention. So instead, what we've done is create this regulatory mechanism that I'll tell you about in a little while. So and we also then look at a utility function to allow for these more general responses that incorporate deaths and recoveries, and this looks at alternative imperatives for intervention. So the idea here is to be able to identify key features that differentiate countries that have experienced a severe outbreak from those that have managed to contain the spread. So we'd like to be able to identify those differences between the countries. We start with a simple stochastic SIR model, which has susceptible individuals, infected individuals, and removed individuals. And at each of the individual level events, then we may have a susceptible and an infected move to two infecteds at rate alpha, or an infected move to a recovery with rate beta. So we have alpha and beta are our rate parameters, and we have this discrete state continuous time Markov process to describe this, this model. So we can simulate then exactly if we have this kind of model using a Gillespie method or other approaches. But the problem with this is that this is too simplistic for many cases, and certainly for our case. So in reality, what we have is unobservable populations with a lot more dynamics. So we have a latent states, which are our susceptible, our infected, and our removed. And we also have our observed states. So we have the confirmed active cases, active confirmed cases, our case recovery, and our deaths. And then we have now individual events that are just expansions of what we saw before, but now we have a number of different rate parameters here, alpha, beta, gamma, and delta, and we have a scale parameter, eta. So you can see here the moves from different states to other states being governed by this rate, by these rate parameters. Now, in order to model then the community response, what we do is we have the transmission rate is going to be a function of the observables. So now we have our individual level events, but if you look before, what we had was a susceptible and an infected moving to two infecteds with rate alpha. What happens now is that we have the susceptible and infecteds moving to two infecteds with this function G. And this function G is going to be dependent on the number of active, recovered cases and the number of deaths. This means then that this is like a regulatory mechanism. So as the number of cases rises, then this G function comes into effect and can reduce the number of infecteds going forward. So this is like the effect of an intervention being governed through this function here. So this introduces a feedback loop into the model, into the system. And so this transmission rate then is going to have this kind of form, this G function is going to have a residual transmission and then this regulated transmission. And this regulation function, this F of ARD, is where you see this kind of feedback dynamics happening according to the interventions that are imposed in a country. So in particular then, the way that we can model this, this function F is through some utility function. And what we've done is look at that utility function just being a very simple utility function in the first instance, which is just the sum of the active cases, the recovereds, and the deaths. So this is the cumulative case numbers under the idea that as a country, as those cumulative case numbers increase, then the country will impose some intervention. So that then is creating this kind of non-linearity or regulatory function. Now you could change that utility function, and we have in the paper explored some alternatives to that as well. So some more sophisticated utility functions. But the nice thing is that we can, in this particular formulation, we can look at those different utility functions and be able to identify which ones may be more appropriate for the system at hand. So the way that we can model then this community response, if we look at this function here, F, it depends, it has a utility function to the power n. And so this n then is really the community tolerance to the rising case numbers. So a country that has so it can determine countries' low tolerance or high tolerance to case numbers. So is the country going to impose interventions early or later in the time course of the infection? I'm just getting my time back on here. Right, so this is the way that we can see this. So a larger n then will result in a smaller c, number of cases, for the regulation to take full effect. And here we see the role of alpha naught and alpha parameters is also important. So this is like how much uncontrolled transmission is going to be in the system, even given the strong regulation parameter. So the thing about this model is we have this discrete state continuous time Markov process given by the first formula you can see there. And you can see that this then is just an initial state vector, and then we're going to have the state change that occurs under the event J. And the Y here is a non-homogeneous Poisson process for the event J with a time-dependent rate that you can see there. Now, we could generate exact realizations using event-based simulation, and that's done in many cases and for COVID-19 modeling as well. But this can be prohibitively expensive, especially in a Bayesian computational approach, which we'll talk about in a minute. So what happens then is we can use a first order approximation to this integral in a tau leaping algorithm. And so instead of having the integral, we have a summation now, and that summation is going to be over Poisson counts, the number of events that occur in a particular interval, t to t plus tau. So we looked at tau, sorry, to be a half a day, and we had some initial conditions based on the Johns Hopkins University data that we used, and so you can see the formulation there. So this then made the algorithm, it's an approximation, but it's much faster to compute. And the way that we looked at the inference then was in a Bayesian framework. We wanted to infer the model parameters, theta here. So we have this set of parameters using the time series data that are available from the Johns Hopkins University website. So the time series data that are available there are the number of cases, the number of recoveries, and the number of deaths at each time period. So we took our first day being the day exceeding 100 cumulative confirmed cases. We undertook inference in a Bayesian framework, and because we're in this with this kind of model, we can't do direct inference, so we're going to do approximate Bayesian computation, a likelihood-free approach. So a brief summary of approximate Bayesian computation: instead of generating theta, the parameters of interest, directly through, like for example, through MCMC, we either have a likelihood that's too complicated or unavailable to us. So what we do instead is, in this sort of model that we've developed, it's very easy to see, like given the parameters, we can simulate some data. So what we do then is, given a set of parameters, we can simulate a set of data, ds, the simulated data. We can compare that simulated data set with our observed data set. If they are close enough in some sense, then we would accept that parameter or that set of parameters as being possibly able to have realized or generated the observed data. So what we do then is we can simulate or propose a parameter set, theta, simulate some data, ds, compare ds to d if it's close enough in some metric rho, and the close enough being governed by epsilon. If that's close enough, then we would accept that value of theta. So we sample the prior theta star, we simulate some data, and then we accept if the metric rho, the distance between our data d and our simulated data ds, is less than epsilon. The challenge here is that that epsilon should be small, but we have many stochastic simulations that are required in order to get an accepted sample. So instead, you can use sequential Monte Carlo for ABC, an extension of ABC, and this involves SMC, sequential Monte Carlo, ABC, particle filtering, and importance sampling. So we put that together, and what we do, instead of just having one epsilon, we have a series of epsilons now. So each epsilon is increasing in steps. We'd like epsilon m, capital M, but we increase the epsilons because that's going to increase the distance between our observed data and our simulated data for which we would accept theta. So we would have more acceptances under a larger value of epsilon, but of course then we want to drive that epsilon down to a relatively small value, epsilon m, and then we would be able to just take our thetas that would have much more with higher probability generated our data. So this means then for each time period or each t, each particle set, we have simulator theta from our prior, and then we simulate some data given that theta, and we keep simulating our data until we end up with a difference between this metric rho of d and ds being less than epsilon 1. And then we set some weights just on the thetas that we've drawn, so that's 1 on n. Then what we do for each of the next steps is we're going to pick a theta I star from the thetas from the previous step with probabilities wj from that step. And now we generate a new theta I for our current step t, and we generate that from some kernel for theta I given theta star. And then we have our simulated data again until the metric or the distance between d and ds is now less than epsilon t. So this is for each of the epsilons we go through this. And so then we set our weights accordingly. We re-weight, that's the importance sampling step. So this is just a way of having importance sampling and this sort of the shrinkage or the different steps for the epsilons. So if we do this then, this sequential Monte Carlo, we end up with a faster approximation and a closer approximation. So just a toy example here. If theta is uniform between -10 and 10, we have a likelihood f of x given theta to be this mixture that you can see here. And the goal is we want to approximate the posterior of theta for just one observed value x observed, which equals 0. So what we do then is that we say, okay, well, we're going to sample from theta, from our prior for theta, from a uniform. We then generate a data, an observed value of x from our likelihood here, or from our posterior, and then we're going to accept the value of theta if that simulated value is close enough to our observed data, which is 0 here. So you can see in red here the values of theta that would actually be accepted under that rule. And you can also see in the right now the ABC SMC distributions, or the distributions generated under this algorithm for different tolerance schedules. So for epsilon 1 equals 5, epsilon 2 equals 1, epsilon 2 equals 0.01. And so you can see how we can really drive in by using this ABC SMC approach. We can really come up with a very tight estimate of theta under this approach. So it's an approximation, and it can be fast, but it can also be a very close approximation. And you can see under the, it's also, this is an example of the number of particles that need to be generated in each step. Under ABC, we have about 4,000 particles if we just use the one value of epsilon. But if we use this ABC SMC approach, we only need 770 particles using the 3 values of epsilon there. So this approach then has been very popular in the ABC approximate Bayesian computational world, and there are many variations on this. Lots of different kinds of adaptive adaptive SMC-ABC approaches. For example, instead of just using, well, you can see on the left there, there's the likelihood, which is a mixture model. You can, instead of using a prior for theta just coming from a uniform, you can also have that being adaptive. So that could be a mixture distribution, and it can also depend on the previous iteration. So in our model then, we employed this SMC-ABC. We used a discrepancy metric, so that rho there between the difference between the data and observed data and our simulated data, just being the difference between our observed A's, the active cases, and the number of active cases we simulate with a particular set of parameters, the recovereds versus the recovereds that we simulate, the observed deaths versus the deaths that we simulate. So this metric then is how close are we to, based on if we draw a theta, then how close are we from the simulated numbers of deaths, recovereds, and cases compared to our observed deaths, recovered, and cases. The SMC-ABC algorithm that we use is one developed by Chris Travanti and Tony Pettit here at QUT. This adaptively selects the acceptance thresholds and uses MCMC steps with Gaussian random walks for the move steps. And the details are given in the supplementary paper for the supplementary document for the paper. We can also compute, this is not so much about implementation, but we can also compute the basic reproduction number here, R0, and the basic reproduction number after regulation as well. And we do that through a system of linearization and then looking for the dominant eigenvalues. So coming then to some results. So this is our model fit. We have the model fitting for Iran and for Italy. You can see here the numbers of cases, recovereds, and deaths here, and the data with a 95% credible interval here. These are some other countries. There were 103 countries that we fitted using this approach. So I'm only showing a couple of them here. So we have China and South Korea as well. And I wanted to show you this because what we see from this is a good fit for some of our countries, and also some of the challenges in fitting the data as well. So in the China diagram for China there, you can see a disjunction in the number of cases, and that's because there was a change in the reporting. This kind of changes in the data impacted on our ability to model for some of these countries. These are the model fit for Australia and for Italy, for the United Kingdom, and for China, as I said. I just thought I'd show you this for the parameter estimates. We get the marginal posterior densities. These are box plots for all of the 103 countries. We get the marginal posterior densities for the parameters. Here you can see two of the parameters of interest and what those posterior densities look like for each of the countries. So this can provide some information about the differences between the countries with respect to these parameters. And another way that this can be visualized is to look at the comparisons between the parameters. So we have different combinations, pairs of the parameters, the response strength, the relative initial undocumented cases here, and you can see the different pairs of parameters and where the countries sit with respect to those pairs of parameters. So you can see, for example, countries with large case numbers often have a low N. And so the low N means a low response strength, and often this high relative initial undocumented cases. China and South Korea recovered quickly as well. So you can see some answers there. That's to the 31st of March. When we look then for an extra 2 weeks, we have until the 13th of April, and we repeated the analysis to see what changes there would be, because from the 31st of March to the 13th of April, we saw many countries introducing interventions, and so we saw a change in the shape of these curves. And you can see here, in light of the new data, many countries have a lower value of n than the response than earlier results implied, but you also have this lower kappa and the lower gamma as well that indicate increased testing and contact tracing. Just another representation of this to show the change then from the 31st of March to the 13th of April in these parameters for the different countries. And so in this way, then we can start to learn something about the different behaviours of the countries and the different effects that that had on these on the number of cases and deaths. And finally, the efficacy of response here. So this is the regulation. This is a plot of the relative regulation strength versus the reduction in the reproduction number. So you can see this plot here really pulling out Singapore and Taiwan here. So many of the most affected countries significantly reducing the reproductive number, but some of the regions, for example, Singapore, during this period, just to the 31st of March, had strong regulation, but almost no reduction in the basic reproduction number. So you can see here, there was a very low change in the very low relative reduction in the reproduction number, and a very high regulation here, relative regulation. And similarly, then there are the similar comments that can be made about Taiwan. So they really stood out from the other countries. So taking these results then, what we've done is we've characterized our model as this broad assessment of the global response to the COVID-19 pandemic. We've had this regulatory mechanism that reflects how countries in the early phase of the outbreak may have adjusted their strategies to reduce the time to recovery, and we've used likelihood-free schemes to be able to solve the inference problem. What we found overall is that many countries with large case numbers had a low value for the regulation parameter. In other words, countries that acted later had higher numbers. In retrospect, hindsight is a great thing. This is, you say, well, that makes sense. So rapid recovery then corresponded to a high identification rate and lower initial undocumented cases. So very severe outbreaks were characterized by a high tolerance to rising confirmed case numbers. So less action until there was a large number of cases, and a high tolerance before significant reductions in transmission rates occur. So for the countries that had large numbers, what we see is this sort of low tolerance to those increasing numbers. There was a lag in putting in place the intervention of measures. We also found that of the top 10 severely affected countries with respect to cumulative cases, the only countries that observed a decrease in active countries during the period of study, this is just until the 13th of April, then, which were China and South Korea, were characterized by high identification rates. And this was the result of highly effective identification and quarantine programs. For many countries in this period that we considered, the transmission rates in the later period of the study were declining, but there could have been large unobserved infected population counts, and these were estimated in the model. So based on our analyses then, what we suggested, and of course this is what's playing out now, is increased testing, contact tracing, isolation and quarantine measures. They are effective in reducing the severity of the outbreaks worldwide. The unknown magnitude of undocumented cases substantially impacts the uncertainty in predictions, and wider testing is essential to reduce this uncertainty. And that's what we're seeing now in most countries. Now that brings us then to the extensions for this work. So we have a number of extensions in play at the moment, and I'll just briefly touch on these. So we have looking at these parameters that we have now, these 8 parameters for each country, we could look at clustering those, doing a more formal comparison, or not formal comparison, but a different kind of comparison between the countries by clustering the countries with respect to those model parameters. So this is work being undertaken by Richie Nyack, a professor in computer science here at QUT, and our team on this, a team of authors on our paper. And the idea here is to use clustering techniques, so k-means and hierarchical clustering and so on, just to see which how many clusters are identified based on these parameters, and then what's driving those different clusters. So what we're seeing at the moment is that there's about 3 clusters. One of those clusters is quite small, and it's really characterized by a quite different combination of parameters compared to the other 2 larger clusters. What we're also doing is taking the air traffic data that has been provided to us by OAG, so that's daily flights for between countries that we had in this analysis, and that's the daily flights over this time period, and devising metrics based on that network of flight. So that flight pattern or the flight network, we can derive summaries from that, and then we can incorporate those summary statistics or summary parameters into our model into our clustering. So we have our model parameters, we have our network parameters based on the flight data, and then we can look at clustering of those. What we see then, and these are results still to be confirmed, but what we see then is a different clustering that is, and when we plot that clustering then on a map, we actually see that reflection of where the cases may have come externally into a country based on the flight data. So it's interesting work, and it's bringing together the mobility data or the flight or through flight data to the epidemic or the epidemiological model as well. The second extension is evaluating coordinated strategies for relaxing restrictions. So if we take the kind of model that we fitted now for the 103 countries and we go, okay, well, what can we learn? So what we've learned is something about the increase and the trajectory of the curve based on interventions for this particular pandemic, and some of those learnings will be useful to take forward to other future epidemics or future outbreaks. What can we learn about the relaxation of restrictions in terms of, okay, we understand something about these curves. If we relax restrictions and we do it country by country, so each country has its own deliberation, its own decisions about relaxing restrictions, versus if there are groups of countries that make decisions about relaxing restrictions, versus if there is a global coordinated approach to relaxing restrictions. So what difference will that make in terms of the transmission, and also then, because we can have local transmission, we can have transmission into and out of countries according to the transport data. And then we can look at, well, what's the difference in those different strategies with respect to the cases and deaths. The third extension is working with Queensland Health here on their escape from COVID plan. So that's been an interesting series of discussions and using Telstra data and Optus data, traffic data and health data to be able to evaluate different strategies for relaxing the restrictions here. And so Queensland Health has been calling this their escape from COVID strategy, colloquially. And so the fourth extension is a different kind of approach. And we've been just exploring how we might think about COVID-19 trajectories as Hawkes processes. So this is this non-parametric and parametric, continuous time, and also discrete time. So it's interesting with discrete time Hawkes processes. What can we say about that kind of model, and how might these models actually be applicable for describing the COVID-19 data? So this is work by a PhD student here, Raihar Browning, and then also in collaboration with colleagues Judith Rousseau and others at Oxford in the UK and Dauphine in France. So the Hawkes process then is this there's variations on the way that we might describe it, but it's we may think about having an outbreak and then having subsequent smaller outbreaks as a result of that main one. And if we have these kinds of peaks and then subsequent smaller peaks, and then we have a number of those. So you think about, for example, earthquake data, there's an earthquake and then tremors after that. And then you might have multiple earthquakes happening. And so you've got this shock to the system and then aftershocks. So is that something, these models have been fitted to other epidemic data. Do they fit to the COVID data? We're still exploring that at the moment. What it looks like is that we need to have quite flexible parameters and also look at what the underlying assumptions might be for the discrete time Hawkes process, but that's still also work in progress. So if any of you are interested in some light relief, we created a game. So it's a game for COVID-19. This is called Stop the Spread. Jack Ford Morgan has and his colleagues have a small games company. He works at QUT making games from our research. This is a cut out. It's for schools and kids. So if you've got kids at home, you can print it out and or play it on the screen. And it's a very simple game to look at epidemics and what happens if you actually then have some sort of intervention in the epidemic, and what does that mean for the increase in numbers of cases and deaths. So just as a light relief, you might be interested in that as well. And again, acknowledgements to my co-authors, and also acknowledgements to ASIMS, the Centre of Excellence in Mathematical and Statistical Frontiers, and our QUT Centre for Data Science, the Data Science at QUT Network, and our Australian Data Science Network. And I'll leave it there. Thank you, Mania.
Yeah, thank you, Kerrie. Was a very interesting talk. I think we have lots of time for questions. So if people could just maybe go to the participation menu and just raise their hand, and then I'll select a few who can. I think Sally was the quickest, so I'll just unmute you and you can. So, yeah, Sally, you can speak now.
Okay, hi. Am I unmuted now? Yeah. Thanks, Kerrie, for a really interesting and thoughtful talk. It was great. I noticed you've got everybody listening, so I think that's also terrific. Look, one of the questions I had was actually about the data itself. I've been working with some people in the US and using the Johns Hopkins data. And there's several versions of it. There's the raw time series, there's the raw data, the time series data, and at the beginning they're quite different. Sometimes, there are negative amounts, so people are resurrecting
That's right.
from the dead. And probably one of the biggest things is...
My husband was very excited about that, by the way, Sally. He was saying zombies.
So the, and it's got seasonality, which is not really seasonality in the sense that people don't die differently on different days, but the reporting, lag between what happens on a weekend and what happens during the week. Could you just talk a little bit about, what did you, so we've found that one of the biggest problems is actually just the quality of the data, which is quite surprising given the severity of what we're facing. and how getting high quality data is, you know, even from John Hopkins, is really difficult. It's messy, and you have to really make decisions about how you're going to deal with all these things. Could you talk a bit about, was that a problem in any of your modelling, and how did you deal with it?
Yeah, thanks, Sally. So it's a really big problem, and I think that one of the issues, it's been an issue that's really been highlighted by this pandemic. The need to have high quality data in a very timely manner, and I think that that's really highlighted some of our profession, for example, why we would need to be in the room, I guess, for collecting these data and being able to assess its quality and then being able to use it, or being able to account for the quality in the analysis. And I agree, the Johns Hopkins data was available very early on. There are alternatives, the European data, which we ended up using for some of the other assessments that we're using now, for example, for the Hawkes process work. Also looking at smoothing over the time period. So instead of looking at each individual day, as we did in this analysis, in the Hawkes Hawkes process analysis, we've been looking at 5-day or 3-day, 5-day and 7-day sort of smoothing, because some of the countries also report, even some of the data sets are being reported at a weekly level, but on a Sunday. And of course, the Sunday is the day when the number of cases is going to be lowest in the week. You know, Mondays and Tuesdays when people get reported. So this is a problem. You could include an uncertainty in the model and take some account of that. So it's like, you know, some misclassification or some extra uncertainty for that.
Yeah, I wonder just how much those choices, like I know a lot of modelers, you know, you look at it and it's sort of crying out for smoothing, but you ask yourself, well, you know, does the choice of smoothing technique affect inference? Had I used something different, would I have got a different result? So these are the sorts of things.
Absolutely. Yeah. So I think there's a whole lot of things around that. So there's, if you smooth temporally, also if you allow for some just uncertainty because of the difficulty in the data, but then also we could look at some, you know, model averaging approaches or some ensembles to get a sense of whether these inferences are really robust to the quality of the data. I don't know, does anybody else, I mean, the great thing about Zoom is that anybody can join in to the conversation. Does anybody else have some comments about that?
Data quality.
About data quality.
So you're all muted, but please, if you have comments, just raise your hand and I can unmute you.
I know that some other people on this call have been analysing some of the COVID-19 data, so maybe they have some comments as well. But it's a very good point, Sally.
Yeah, thanks.
Yeah, thanks. Are there any other questions or comments? Yeah, I don't think so.
No? Okay. Minnie, I'll just come back to that point then, because I'd like to ask the people, I mean, there's many people on this call who analyse data, you know, that have difficulties or difficult data, and data with variable quality. And I think one of the questions then is, for the people who do this, like, do you think that it's something where we should be analysing data that have these quality issues because at least it's better than nothing, or is it actually misleading, and therefore as statisticians or as data analysts, when we should say, well, unless we can clean up the data, then we shouldn't be doing the analysis? I'd just like to know people's opinion.
Thanks. Sally, you're still raising your hand, but I'm not sure whether there's a comment.
Yes. Okay, I'll ask another question. I think that these are really interesting. I mean, obviously I'm interested in because I keep asking questions about it. But, you know, I think that when you're dealing with a pandemic, you go with what you've got. But I do think it really highlights the need for actually serious data collection and data cleaning, you know, in future and making it accessible. I suppose what I wanted to ask was that, have you looked at your methods by comparison to any of the other sort of models that have been out there? Have you looked at how your methods compare in terms of the forecasts with, there's this one, the IHME one, which sort of seems to be getting uncertainty quantification all over the place, but that's another issue. But so have you sort of looked at yours and how it stacks up to others, and you know and you know, because you talked about ensemble methods, so what could be gained by looking at what you're doing with basically something like what's coming out of IHME or YYG? That's the MIT one.
Yeah, thanks, Sally. So for those who aren't as close to this, then the IHME is the Institute for Health and Health Measurement,
Health data
evaluation.
Yeah,
that's right.
University of Washington.
Yeah, that's right. So so they've been doing a lot of the modelling for the US, and one of the good things about the IHME Centre is that they have published their algorithm or their model and their data, and it's all open. So that's not the same for other groups, including Australia. But so that's been very good. The thing is that there are great concerns about that model, and so they've been expressed in different forums as well. And I think the models actually provide some different insights, and so I think one of the ambitions may be to not only do the model averaging for prediction, but also to understand what the models actually inform us about. So some of the models are very good for accurate prediction, or sort of better for accurate prediction, but even understanding that prediction in this case can really only be about 3 days, maybe a week, but otherwise it's very difficult to predict in this environment. And but you can also get different insights. So what we were looking at in this model, for example, is just what is this relationship between what we're calling this regulatory mechanism and this is smooth function that takes into account the different interventions. Other models will have different ways of or different parameters that they'll focus on. So I think, if we had looked at those different approaches and sort of pulled out what the different insights are that we're getting from those models, and then maybe that would be something that's interesting. What's the collective insight from these models? So for example, if you fit just even a simple multinomial autoregressive model or a Poisson model to these, you get some insight into the trajectory of the data, and from the multinomial autoregressive model you can actually get quite a good fit. The multinomial being, cases, recovered deaths, and then you follow that through as with an autoregressive model.
Yeah.
Thank you. I see that Louise is raising her hand, but you don't have a mic. You don't have, I think, audio on, so I can't unmute you without a microphone. But you can write something in the chat if you have a question, or otherwise, if there's no other person, so maybe we close it then. So thank you, Kerrie, again. I think it was very interesting, and it seems you're doing lots of exciting work. And so
okay.
Yeah, thank you.
Thanks very much, Minnie. Thank you very much, everybody, for attending. Bye.
Thanks. Bye.